Hi, this is Dr. Shoikat Majumdar. In this video lecture, we will discuss optical lenses. It is under basic physics course in Diploma Engineering. Optical lenses is under submodule 4.3 of Unit 4 and the unit name is Light. Learning objectives. After completing this module, we should be able to determine the focal length of converging and diverging lenses. Apply the Lensmaker's equation to find the parameters related to the lens construction. Use ray tracing techniques to construct images formed by converging and diverging lenses. Find the location, nature, and magnification of images formed by converging and diverging lenses. So, in our previous lectures, we know the converging and diverging lenses. Here is a small recapitulation of the previous lecture. So, if a smooth surface replaces the prisms, a well-defined focus produces clear images. Here it is a converging lens. Parallel rays are coming and falling onto the lens, and this lens producing the incoming light to converging one, and all the light rays are meeting at a particular point. This point is known as a focus. It is a real focus. So here in this figure, this is a double convex lens or biconvex lens. But here in a double concave lens, if parallel rays is falling onto this one, it looks like that the rays after refraction are diverging from this point. This point is known as a virtual focus. Focal length of the lenses. So the point F from the optical axis, the distance of F from the optical axis is F, and here it is plus F. If our eye is along this direction, then it is plus F. But here for diverging lens, this distance F, it is minus F, as it is producing behind that lens. That means eye is along this direction and it looks like the light is coming from this point. So here the eye is here, so F is minus F, opposite to the eye. Or the direction of ray is here and focus is here, so that's why it is minus F. The focal length F is positive for a real focus and negative for a virtual focus. So for diverging lens, this focus is a virtual focus, so it is negative for diverging lens. Principal focus. Since light can pass through a lens in either direction, there are two focal points of each lens. This is already we have discussed. The principal focus point, here it is F, as the light is coming from this point, this end, and after refraction the light is meeting here. This is the principal focus. So again there is another focus, the yellow one. This is the secondary focus. If light is coming from this direction, so here it will meet after refraction. So for this end of the lens, this is the primary focus or principal focus. This is for this lens, this is the secondary focus. Here for diverging lens, this is the principal focus, this is the secondary focus. Now suppose light moves from right to left. This is the, for this one, this is the primary focus, this is the secondary focus. Here this is the primary focus, this is the secondary focus. Types of converging lenses. In order for a lens to converge light, it must be thicker near the midpoint to allow more bending. So for double convex lens, at the midpoint it is thicker. For plano-convex lens, the midpoint is thicker. For concave lens, this is also thicker. So double convex lens, plano-convex lens, converging meniscus lens, all will converge the light. So diverging lens. So in order for a lens to diverge light, it must be thinner near the midpoint to allow more bending. Here it is thinner for double concave lens, it is also thinner in the middle, and for diverging meniscus lens it is also thinner at the midpoint. Lensmaker's equation. The focal length f for a lens can be calculated from the Lensmaker's formula, and the formula is 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. So n is the refractive index of the material of the transparent medium or lens. R1, this is the, for this curvature, this is the radius of curvature. So for this one, this is R1. That means if light is coming from this direction, so the lens on which at the end on which the incident ray is falling, that's radius of curvature is R1, and the end from which the light is emerging out, that's the radius of curvature is R2. So 1 by f is equal to n minus 1 by r1 minus 1 by r2. So for this lens, this is the concave convex lens. Here on this concave end, this one is negative and positive for convex end. This is the sign convention. So here for this surface, the radius of curvature is R1. This is for the incidenting surface. If light is coming from this direction, this is the incidenting surface, so this one is R1, and if light is emerging out from this surface, so this is its radius of curvature is R2. Signs of Lensmaker's formula. So here for this lens it is minus as it is concave surface, and for the convex surface it is plus if light is coming from this direction. R1 is the radius of curvature of the lens surface on which the rays are incident. R2 is the radius of curvature of the lens surface from which the rays emerge after refraction through the lens. Focal length f is positive for converging and negative for diverging lenses. This is the formula. 1 by f is equal to n minus 1 by r1 minus 1 by r2. So for this surface, this concave surface, this one is minus 1, and this convex surface, this one is plus 1, positive, plus. This one is plus, this one is minus. Let us take an example. A glass meniscus lens of refractive index n is equal to 1.5 has a convex surface of radius 40 cm. Here in this concave surface. So here in this figure, this is the concave surface. Its radius of curvature is 40 cm. And a convex surface, this is the convex surface. Its radius of curvature is 20 cm. It is 20 cm. So for this concave surface, this is minus, this one is plus. So R1 we are writing here, it is 20 cm, and R2 is equal to 40 cm. As this one is the R1 means for this one. For this one is R1, for this one is R2. So this is R1. That means when the light is incidenting, this one is here, this is 40 cm, this one is 20 cm. So if we put these values, n is equal to 1.5 minus 1 into 1 by 20 minus 1 by 40. So this becomes 1 by f, 1.f minus 1. So this one is 2 minus 1 into 0.5 by 40. So f becomes 80 cm and it is positive. So it is a converging lens. Another example for this planar convex lens. What must be the radius of the curved surface of a planar convex lens in order that the focal length be 25 cm? So for this surface, this is the surface, its radius is R1. This is the surface, its radius is R2. As it is a straight one, so plane, so its radius is infinity. And R1 is supplied, it is 25 cm. So 1 by f is equal to n minus 1 by R1 minus 1 by infinity. So 1 by infinity means 0. So 1 by f means 1 by 25 is equal to 1.5 minus 1 into 1 by R1. So R1 is equal to 0.5 into 25 cm. So it becomes R1 is equal to 12.5 cm. So, and it is a convex lens. The convex surface, it's positive. And this is the radius of curvature of the convex surface, and it is positive. Image tracing points. Already we have discussed in our previous videos how the image are traces out. Draw an arrow to represent the location of an object. Then draw two of the rays from the tip of the arrow. The image is where lines cross. This is the arrow. There are two rays. One is parallel to this one. It is coming, passing through the focus. Another one is passing through the optical center. They are intersecting. Another one is passing through the focus, parallel to this one, parallel to the principal axis, and they are meeting at this point. The image is formed at the intersecting points of these three. Is the image erect or inverted? Is the image real or virtual? Real images are always on the opposite side of the lens. This is the real image. This is the real image. Virtual images are on the same side. If the object is here and the image is produced in this side, then the virtual images are formed. Here in this figure, this image is real one. It is opposite to the object. It is enlarged, diminished, or same size. We have to find out. Suppose an object is outside 2f. Then from the tip of this arrow, the light is passing parallel. After diffraction, the light will pass to the focus. And the light that is passing to the optical center, they are meeting here in this point. And the object is produced in between f and 2f. So this, the image is produced in between f and 2f. So this image is inverted. This one is real and size is small. So diminished image is produced. So here image is inverted, that is opposite to the object orientation. Number 2, the image is real, that is formed by actual light rays in front of the mirror, and the image is diminished in size, that is smaller than the object. Image is located between f and 2f. Now if the object is placed at 2f, so this light from the tip is parallel passing through f. This light ray will pass to the optical center meeting at this point. So image is produced at 2f. So the image is inverted, that is opposite to the direction, opposite to the object orientation. Number 2, the image is real, that is formed by actual light in front of the mirror, in front of the lens actually. There is a typographical mistake. The image is same size as the object. So in a nutshell, here the image is real, inverted and same size, and image is located at 2f on the other side. Object between 2f and f. So here object in between 2f and f. So this light is passing parallel to the principal axis after refraction passing through the focus. Here it is passing through the optical center, they are meeting, and the object, the image that is produced beyond 2f, and it is inverted. So this image is real, inverted and enlarged. Why it is inverted? The opposite to the object orientation. Object is around this direction, it is around this direction. The image is real, formed by actual light rays on the opposite side. The image is enlarged in size, that is larger than the object. Image is located beyond 2f. Object at focal length f. Here the object is placed at the focal length. Now this ray is parallel to the principal axis, will pass to the focus, and this ray will pass to the optical center. They will not meet. So when the object is located at the focal length, the rays of light are parallel. The lines never cross and no image is formed. So parallel rays will produce, that means the image will be produced at infinity. That means it will not meet. It looks like it will produce at infinity. We will not get any image. So there will be no image formed. Object inside f. So object is in between the optical center and object is here. Now what happens? This one is parallel to the principal axis, will pass through f, and this ray will pass to the optical center. So if it also here in this direction, it will not meet. It is going outside. Now if we extend beyond this, then what will happen? It will meet or intersect at a particular point. So then an image is produced here. So this image is beyond the lens and towards the direction where the object is placed, and it is larger in size. So image is erect and same orientation as the object. Number 2, the image is virtual, formed where light does not go. The image is enlarged in size, that is larger than the object. So image is virtual, erected and enlarged. Image is located on near side of lens. This is the near side of the lens. So review of the image formation of biconvex lens. If we place the object in between optical center and the focus, the image will be virtual, erected and enlarged.